Today we have Lingfu Zhang, and it's going to discuss about temporal correlation in the last passage percolation with flat initial condition. So, please.
Okay. So thank you everyone for coming to this talk today, and thanks to Mathieu for inviting me. So today I'm going to talk about work about the time direction correlation structure for the well-known exactly solvable last passage percolation model with exponential weights. And we look at the flat initial data case. So such question was first interested by the physicists, and there was some questions asked by Ferrari and Spohn a few years ago. Well, many of them have been answered, and this is one of the remaining cases. So this work is joint with Reddy Basu, who is a faculty at ICTS in Bangalore, India, and with Shashendu Ganguly, who is a faculty at UC Berkeley. So it was initiated during a conference in ICTS in India, when Shashendu and I was visiting there. It was like a couple of years ago. It's also the place where I first met Mathieu. So it was a wonderful event. Okay, so let's start. So I will first spend 10 to 15 minutes to talk about the background and set up the problem. Although I suppose that since it's an integral probability seminar, many of you might be quite familiar with this exactly solvable model and know more than I do. But let me just set up these things. So we work on this two-dimensional lattice with IID exponential weight. So at each vertex, you have an exponential one random variable. So for two vertices, U and V, separated in the time direction, meaning that U is less or equal than V in each coordinate, we can define the passage time as the maximum path weight for all directed passes from U to V. So the path can only go up and right. And for all such passes from U to V, we take the sum over the path of the weights, and we take the path with the maximum weight. And that path is also defined as a geodesic from U to V. So this is a very classical setting. So this model is exactly solvable in the so-called QPZ universality class. And I will explain this as using the connection with TASEP. So in the TASEP, you just look at the 1D lattice Z. At each site, you can have a particle or it is empty. And for every site, if there's a particle and the site right next to it is empty, then this particle can jump to the right with rate 1. And for this, we can also associate with the growing surface, so that for each site, if there is a particle, we draw a downward segment. And if it is empty, we draw an upward segment. So if you connect all these upward and downward segments, you get a piecewise linear function with slope 1 or -1. And that surface grows up. So from this connection with TASEP, you see that this surface grew up in a way such that for any downward angle, it flips to be upward pointed with rate 1. Okay, so this growing surface can also be constructed using the exponential last passage percolation, so that initially you have some right down path. We call it B0, and all the vertices that's below this path is said to be occupied. And then for each vertex, if the vertex to the left of it and to the down of it is occupied, then it also becomes occupied with rate 1, and that's independent for all the unoccupied vertices. So in other words, the waiting time for one vertex that is ready to be occupied to being actually occupied, the waiting time is exponential 1 independently. So this gives a growing surface, and so suppose you start from B0, what's the surface you have at time t? Well, that just consists of all the vertices whose passage time to your initial boundary B0 is at most t. So that gives you the boundary, the occupied size at time t. And for that reason, we also call this one direction in last passage percolation as a time direction. And you see that this growing surface is the same as the growing surface from the T-tip if you just rotate by the 45 degree. Okay, so this is that some very classical setups. Now let me just talk a bit about some very well-known like historical results. So it was first by Ross in 1980s where he drew this connection of this growing surface between last passage percolation and T-tip, and he showed that the passage time from 0, 0 to NN is in the order of 4n. And then the next thing is about the fluctuation, and as far as I know, it's by Johansson in 2000, where he showed that the fluctuation is in the order of n to the 1/3, and after this rescaling, it converges weakly to the GOE Tracy-Witten distribution. Then the next thing to study is about the joint distribution of different endpoints, and it was first for the endpoint varying in the space direction. So let's see, you look at the one fixed endpoint 0, 0, and then you allow the other endpoint to vary in the line x plus y equals to 2n. Then that gives you some point to line profile, which is a random function, and the correlation length is in the order of n to the 2/3. And after the rescaling, so you're scaling the time direction by n to the 2/3, and in the magnitude, you rescale it by n to the 1/3. It converges to some profile, which is the Airy-2 process, which is a stationary random process, and the distributions are given by determinantal point formulas, and that for that minus a parabola. And this corresponds to the, so it's starting from the fixed point 0, 0, and that corresponds to the step initial condition in T-tip. So in T-tip, you initially for all negative sides, you have particles, and all positive sides, you have empty. Okay, a similar result is also obtained for the flat initial delta condition. So here, rather than starting from the fixed point 0, 0, you look at all the starting points in the line x plus y equal to 0. And then you maximize over all the passage times from the line to a vertex v. And the maximum passage time is the line to point passage time, and that's, we use xv to denote that. Okay, and for that, if you vary your v again in the line x plus y equal to 2n, you still have a random profile, and the correlation length is again in the order of n to the 2/3. And after appropriate rescaling, that converges again to some random function, which is identified as the Airy-1 process, which again has some determinantal formula process. And more generally, for general initial data, so that rather than fixed point or the flat initial data, you can have some arbitrary initial condition B0. And then for that, as long as the initial data converges to something, then you can also identify the limiting profile, and that's called the KPZ fixed point, which is a more recent result by Maciejewski, Kosto, and Romanek. Okay, so let's go to our setup. So we are interested in the time direction correlation structures. So we look at two vertices. One is RR, and the other is NN, so that they're separate in the 1, 1 direction. So we look at the special case of the flat initial data case. So you have the line x plus y equal to 0, and then you look at all the passage times to RR and to NN, and for each of them, you take the maximum over all the starting points in the line. And the scaling limit we take is that we let R and N go to infinity proportionally. So R is taken as some tau times N, where tau is some fixed number between 0 and 1. And we want to understand the correlation of XR and XN, and how that depends on N and how that depends on tau. Okay, so such two-time covariance was first studied by physicists. So the first work we found is by Sinha in 2005, where they used experimental approaches to do that. And then the physicists also used some simulations and numerical analysis. So in the math community, it was more recent, and by Ferrari and Spohn in 2016, where they analyzed several initial data cases for this problem, and then they made several conjectures on the behavior as tau converges, tau goes to 0 or 1. I will go back to this. But I would also like to mention another series of work, first by Johansen for the Brownian and geometric aspect regulation, and by Bike and Liu for exponential aspect regulation. So they just computed the joint distribution of this passage time to NN and RR, and they get determinantal formulas for the joint distributions of these two time distributions. I would say, like, in principle, from the formula they get, one can compute the covariance by just taking integrals of things. But however, the thing is that these formulas are quite involved and not easy to analyze. In particular, it's hard from their formulas to see like what the covariance is like under certain limiting scheme as n goes to infinity and tau goes to 0 or 1. So, so the question of Ferrari and the Spohn remains. And last year it was by Ferrari himself and Ocelli, and also my collaborators Basu and Ganguly. So this like roughly the same time, and using different approaches, they could prove some covariance structures for this and for the step initial data case. So namely, instead of looking at the point line passage time, they look at the passage times from 0, 0 to NN, and from 0, 0 to RR, which is tau n, tau n. And then they could show that the covariance first is in the order of n to the 2/3. And after dividing n to the 2/3, that converges the limit, the dependence on tau is as following. So when tau is very small, it goes to 0 in the order of tau to the 2/3. And when tau is very close to 1, this converges to some constant at the rate of 1 minus tau to the 2/3. And later, by Ivan Cohen, Permin Gosai, and Alain Hamant, they proved the analogous results for this, for the KPZ equation. So for the solution of the KPZ equation, and also with the step initial conditions, they could compute the covariance of the two-time distributions, and then obtain similar behaviors as this for tau goes to 0 or 1. And also in the work of Ferrari and Ocelli, they showed that this behavior of tau goes to 1 is universal, so that the same behavior of like c times theta 1 minus tau to 2/3 happens if you are under some other initial conditions like the flat one as we see here, or the stationary initial conditions. Okay, so the for the picture by Ferrari and Spohn, one remaining question there is the behavior of this flat initial data condition and the tau goes to 0 scenario. So as already shown there, this covariance for fixed tau, this covariance is in the order of n to the 2/3, and as n goes to infinity, this converges to something which we denote as rho tau. And then it remains to analyze the behavior of this rho tau, like the dependence of it on tau. Okay, so that's our main result, is that we show that as tau goes to 0, this rho tau is actually in the order of tau to the 4/3. And unfortunately, we have this little O1 correction in the exponent, which is due to some subpolynomial error term that we cannot remove, but it's actually an artifact of our approach. And we believe that in the actual case, the actual thing is that there is no such little O1 thing. Okay, so that's basically what we what our main result is, and also the setup. So any questions so far? Okay, very good. So hopefully I explained this things clear. And let me just, okay, so let's go to some more arguments on how this is proved. So in general, our arguments are geometric, and one technique that we use is the Brownian comparison of the area 2 process with the Brownian motion. Okay, so I will explain that. So before going into some more detailed things, I would like to first talk about the heuristic, about why this covariance is in that order of tau to the 4/3 times n to the 2/3. Okay, so here we draw this picture of the line to point geodesic from x plus y equal to 0 to nn, and from x plus y equal to 0 to rr. So these are these two red curves. One classical result about the last passage percolation is that the geodesic has spatial direction fluctuation in the order of n to the 2/3. So the spatial direction fluctuation is just like the 1 minus 1 direction, and how it fluctuates in that spatial direction. So if you look at the 1 to nn, at the end, the ending point should fluctuate in an interval of length n to the 2/3, whereas for the geodesic to RR, the lower ending point, the location should fluctuate in an interval of length r to the 2/3. Okay, so if you denote U0 as the intersection of this long red curve, which is a geodesic to nn, with the line x plus y equal to 2r. So if you let U0 to be that intersection, then the distribution of U0 in this line would be that it fluctuates in an interval of length n to the 2/3. Okay. So typically, the distance between U0 and RR would be in the order of n to the 2/3. So what that means, if U0, condition on U0 is at some place n to the 2/3, this means that these two geodesics would have very little interaction. That's because condition on U0, the part of the geodesic below U0, the spatial fluctuation would be in the order of r to the 2/3. And also the spatial fluctuation of the geodesic to RR would be in the order of r to the 2/3. Whereas the distance between U0 and RR is n to the 2/3, so that's much larger than r to the 2/3. Then that would mean that these two geodesics would be very unlikely to coalesce or to have any impact on each other. So basically, if you draw some yellow boxes here with white r to the 2/3, each of them around this geodesic, then each of them would be likely to restrict it within these yellow boxes just by this the fluctuation estimate. Okay, on the other hand, if U0 is close to RR, well, that happens with probability R over N to the 2/3. Well, that's because we assume that the distribution of U0 would be quite uniform in an interval of length R to the 2/3. So for the probability that U0 is in some R to the 2/3 neighborhood of RR, that would be R to the 2/3 over N to the 2/3. Okay. And then in this scenario, when U0 and RR is very close, then the part of the geodesic below U0 and below RR, they would be very likely to coalesce very soon. And then the intersection of these two geodesics would have length in the order of R. That would mean that there is a contribution of R to the 2/3 to the covariance. Since for a geodesic of length R, the variance of the weight would be in the order of R to 2/3, and now you have like the overlap of length R, then the variance would be in the order of R to 2/3. So when you averaging over these two scenarios, so that you multiply this probability with this contribution, and in this scenario, we just assume that there's no contributions to the covariance, then you would get that the covariance is in the order of R over N to 2/3 times R to 2/3. So that just corresponds to, so if you remember that tau is a ratio of R over N, then this just corresponds to tau to the 4/3 times N to the 2/3. Okay, so this is just the heuristic level explanation of why the covariance should be like that. So I guess if I'm giving like a 30-minute talk, it would be a good place to stop. But now we have some more time, and we can talk about some more proof details and the approaches that we use to rigorously establish this heuristic. So far, any questions? Okay. So the general approach is to make this heuristic rigorous. For that, we would construct the geometric events about the geodesics and to bound the passage times, which is the weight of the geodesics, and also the transversal fluctuations. The main tool that we use is from the integral probability, so that for the passage time from 0, 0 to Mn, where here you need to assume that the ratio of M over N is not too weird, so that it's roughly in this 1-1 direction. So the passage time from 0, 0 to Mn is this constant plus an error term of n to the 1/3. And most importantly, there is exponential decay when you deviate a lot from the mean. Okay, so how would that be useful? Well, this is just the basic bracket which we use repeatedly in our argument. So let's go to some more rigorous analysis of this picture. So in practice, what we do is that we use Umax in the place of U0. So recall that U0 is the intersection of the point to line geodesic from x plus y equal to 0 to Nn with the line x plus y equal to 2r. Well, in practice, what we do is that we take the Umax, which is the lower end point for the geodesic from x plus y equal to 2r to Nn. So we will say that this Umax is a very good approximation of U0. And there are several advantages of using that over directly using U0. Basically, if you look at this Umax, it only depends on all the random fields above the line x plus y equal to 2r, whereas the passage time to RR only depends on the random field between the two lines. So this Umax and the passage time from Umax to Nn is basically independent of what's happening between these two lines, and that's independent of XR.
I'm sorry, can you repeat what is Umax again?
Oh, so Umax is that you look at all the endpoints in x plus y equal to 2r, and consider each of them the passage time to Nn. And Umax is the point where this passage time is maximized.
I see. Okay.
Thank you. So yeah, so basically you can just look at all you just take the point to line geodesic from this line x plus y equal to 2r to Nn, and the Umax is just the lower end point. Okay, so we want to use this Umax to approximate U0. And to do that, one property we use of the point to line profile is that, okay, if you move away from this Umax in the spatial direction, then the passage time to Nn decays at least square rootly. Okay, so that's a property that's from the asymptotic limit. So as we say that the point to line profile converges to the Array2 process. And okay, so there is some argument, some result saying that the Array2 process should be like Brownian motion locally. So this means that, okay, this line to point profile locally around Umax, it should look like around the maximum of the Brownian motion. So that means that when you move away from this Umax, the passage time should decay in the order of square root of the distance that you are away from Umax. So that's it. Suppose your Umax is the distance from Umax to RR is much larger than R to the 2/3. This means that for a vertex near RR, the passage time to NN compared to the passage time from Umax to NN, the difference is at least R to the 1/3. Okay, while if you look at the geodesic between these two lines, so this part, the fluctuation is at most in the order of R to the 1/3. This means that for any geodesic from NN to somewhere around RR and to the line x plus y equal to 0, the weight should be cannot like beat the weight if you go through this Umax and to this line x plus y equal to 0. This means that your U0, which is defined as the intersection of the passage time from x plus y equal to 0 to NN, that U0 should also should not be R to the 2/3 away from Umax. So this means that if Umax is far from RR, then U0 is also likely to be far from UR. And for the same reason, if your Umax is quite close to RR, then the actual geodesic from NN to x plus y equal to 0, it's also likely to pass x plus y equal to 2R at some place very close to RR. Okay, so basically here it just establishes that you can use this Umax to pinpoint where this U0 is, and in our heuristic we can use this Umax to analyze, just to discuss where the Umax is to analyze the contribution to the covariance from each scenario. So one thing that's used here is about the Brownian comparison of the array 2 process. And so as I said, like we use that the point to line profile converges to the array 2 process, and we need to compare that with the Brownian motion. And that's based on the Brownian Gibbs property of the array 2 process, because that the array 2 process is just the top line of the array line ensemble, and so you can have the resampling arguments. While for that, we're actually not doing that. We just use the black box from the results by Kovic, Hamann, and the Heat. I will talk about that soon. Okay, so let's talk about so we prove the upper bound and lower bound separately using different geometric arguments. So let's talk about the upper bound first. So for the upper bound, we show that for R and N such that the ratio is bounded away from 0, the covariance of XR and XN is bounded by this term is like tau to the 4/3, and we also have this n to 2/3, whereas we lose a subpolynomial factor. So you see this factor is R over n to the 5/6, so it's like tau log tau to the 5/6 and take the exponent of that. So that's subpolynomial in tau. So this is an artifact resulted from the tool that we use, which potentially can be removed if we use some better techniques. Okay, so here is the picture again. So we want to say that, okay, it's likely that U0 and Umax is far from RR, and when they are close, the covariance is also upper bounded by R to 2/3. So several things to verify from the heuristic. The first is that where this Umax is uniformly distributed in an interval of length n to 2/3. Okay, because only if this Umax is uniformly distributed, then the probability that it's within R to 2/3 neighborhood of RR, the probability is R over n to 2/3. And we also need to verify that U0 is close to Umax, as we have said. So this boils down to several properties of the array 2 process. First, the Argmax of the array 2 process is uniformly distributed, like roughly uniform distributed in some compact interval. And also around the maximum of the area 2 process, it looks like a Brownian motion condition below 0. So it's just look at around the maximum of the Brownian motion. So for the Brownian motion condition below 0, that's like a negative of a basis 3 process. Okay, so to understand this area 2 process to bound these probabilities using the similar bounds for Brownian motions, we bound the Radon-Nikodym derivative of the area 2 process over Brownian motion. And using the techniques from Covey, Hammond, and Heath, we managed to do this. And in doing this, we lose a subpolynomial factor. And of course, the main result in that paper says that for any event, if under the Brownian motion, the probability is epsilon, then you can upper bound it, the probability of the same event under area 2 process by epsilon times exponential minus log epsilon to the 5/6. So that accounts for this extra factor. And again, this is something that maybe we can remove using better analysis of the area 2 process. Okay, so some slightly more technical details here. So what we do is that we first divide the line x plus y equal to 2r into segments. And each segment, the length is in the order of r to 2/3, but we make them grow polynomially. So the reason that we choose polynomial growth is that to make some estimates to be bounded when you sum over all this j. Then the next thing is that we sample all the randomness above the line x plus y equal to 2r. And so that we first freeze what's happening above the line x plus y equal to 2r. So when you do this, this Umax is already determined. So recall that this Umax is just the maximum of the point to line profile from NN to the line x plus y equal to 2r. Okay, so when you freeze all this randomness above this blue line or this blue dotted line, your Umax is already determined. And then we just condition on the event that the Umax is in some Lj, and also condition on this point to line profile here. And then we study like what's the contribution to the covariance. Okay, so for doing this, we look at, okay, so we consider these two passes. The first is the path from the line x plus y equal to 0 to RR, conditioned within this yellow box. Okay, and the next thing is the path from this line to NN, conditioned outside this yellow box. Okay, for these two passes with a maximum weight under these constraints, okay, since the first one only depends on the random field inside this box, and the second one only depends on random field outside this yellow box, they are independent. And given that your Umax is somewhere at uj for some j not very small, you can bound the probability that the geodesic to NN intersects this yellow box. So basically, you can see that with high probability, the actual geodesic to NN is the same as the geodesic to NN conditioned outside this yellow box. And the geodesic to RR is the same as the geodesic to RR conditioned not except this yellow box. So this means that your XR and NR are respectively close to some quantity, and the quantities they are close to are independent. Then using that, you can bound the covariance of XR and XN, condition on Umax is in some Lj. And then the next thing to do is that you sum over all this j. Okay, and for j not very small, like each of them is very small, and the contribution like decays polynomial in j, so that when you sum them up, then you are fine, and then you can bound this by a quantity that's very small to what is desired to be. And so the main contribution comes from the fact that your Umax is in the intervals close to R. And so in doing this, again, we use the Brownian comparison results. So we need to see that around this, when you move away from Umax, the line to point profile actually decays in the order of square root of the distance you are away from this Umax. And you also need to study the probability that Umax is actually in this interval. We also need some transversal estimate of the geodesic. So basically, yes, we say that we need to bound the probability that the geodesic to RR goes outside this yellow box, and the geodesic to your Umax for Umax far away that goes inside this yellow box. So these are all like the transversal estimates. And for that, using the tail estimate of the passage times, you can establish that for this geodesics, they cannot wander a lot in the space direction. So that's a geometric argument that we use to establish the upper bound. Okay, so the next is about the lower bound. So for the lower bound, we do slightly better, and we can lower bound this covariance by just tau to the 4/3 times n to the 2/3. Okay, but the geometric argument, although the heuristic is the same, but we need to take slightly different geometric arguments here. I need to say that the arguments are developed upon the arguments for the lower bound for the step initial data case and from the earlier work of my collaborators. Okay, so that's the picture here. So you look at this passage time to RR and the passage time to NN. So the idea is to, okay, that's a very high level idea. So you need to construct some event such that the event happens with probability R over N to 2/3. And then this geodesics to RR and NN, like they coalesce a lot. So for this, we draw this very thin green box. So this green box has y theta times R to 2/3, where theta is a very small constant. So we want to construct some events such that this geodesics must go through this green box between these two lines. And then if both geodesics are forced to stay within this green box, then it's very likely for them to coalesce very fast. Okay, so how do we do that? Let me just, so you see these two big green boxes. So for each of these green boxes, they are just right next to these green boxes. And the y is some big constant times R to the 2/3. So for each of these green boxes, we construct the event such that for any path entering these green boxes, the part of the path in this green box, the weight is very small compared to the, just by some big constant times R to the 1/3 small compared to the same, the geodesics with the same endpoints. Okay, so this is some event that depends only on the random field inside these gray boxes. And also that can be constructed to happen with some constant probability. By constant, I mean it does not decay as R goes to infinity. And also we condition on the event such that the point to line profile from x plus y equal to 2R to NN is like the following. So the maximum, which is the Umax, lies somewhere in this upper edge of this green box. And as one goes away from it, it decays exponential, square rootly when one moves away from the RR. Okay, so this happens with probability R over N to 2/3, and we can lower bound that probability. So again, this is to analyze this point to line profile. And for that, again, we use that it converges to every two process, and then we use Brownian comparison. Well, the reason that we don't use a factor, like a logarithm factor, sorry, not logarithm, like a subpolynomial factor here, is that here we are lower bounding things. And we sort of use the fact that this array2 process is stationary, so that you can translate this event to have like n over r to the 2/3 copies of them, and each of them has same probability, so that then the union of them has some constant probability, and that is lower bounded, and then you just divide by n over r to 2/3, and then you recover that each of them, the probability is lower bounded by r over n to 2/3. Okay, so we condition on these two events, then we have that it's very unlikely for the geodesic to NN and the geodesic to RR to coalesce. And more importantly, these two events are independent. So the first event is just the point line profile to the line x plus y equal to 2r. So it depends only on the randomness above the line x plus y equal to 2r. And the second event only depends on the randomness in these gray boxes. So these two events are independent, so you can just multiply the probability. Okay, so the last step is that, okay, condition on these two events, how would we lower bound the covariance? Well, we need to, okay, so rigorously speaking, we need to look at one more thing, which is called x theta. So x theta is just taken as the best passage time for a path from in this green box, so that's from the lower edge of the green box to the upper edge of the green box and constrained within this green box. So this, so this is, we call this best passage time x theta. Okay, then condition on these two events for the geodesic from this line x plus y equal to 0 to RR, that geodesic is very unlikely to enter this gray box. So it's likely that that geodesic would coalesce with this, the path with weight x theta. And also for the geodesic from the line to NN, it's very unlikely to enter this gray box. And when you are moved beyond this gray box, the point line profile would be very small, so it's also very unlikely to go around this gray boxes. So this means that this point line profile from point line geodesic to NN is also very likely to be constrained within this gray box. So that said, if we take this quantity, xn minus xrn, so xrn is just the best passage time from line x plus y equal to 2r to NN. So the difference of these two should also be very close to x theta, since that the part of the geodesic is within this green box, and it's likely to overlap with this x theta. So you see that both these quantities are close to x theta, and on the other hand, you have that the variance of this x theta itself is some big constant times r2 2/3, and you see that this constant grows as your theta becomes smaller. So when your green box becomes thinner and thinner, this variance would become larger and larger. Well, so why is that? Well, you can imagine that your theta is very small, so that you just have one line here, so it becomes a green line. Then the passage time, the best passage time in this line would have like it's just a fixed path, then you have like Gaussian fluctuations. So when it becomes thinner and thinner, then the variance would increase. Okay, so that's it. By taking theta small enough, you can have that this variance to be large enough, and then you can also have that xr and xn minus xnr, each of them is close to x theta. This means that the covariance between xr and xn minus xnr is lower bounded by r2 2/3. And also recall that xar is the passage time from the line x plus y equal to 2r to NN. That is independent from xr. So that gives you that the lower bound of the covariance between xr and xn. So that's also lower bounded by r2 2/3. Okay, so that's a lower bound. Any questions? Yeah, maybe I go through some comments about this. So compared to some previous approaches where you use more integrable probability input, our argument is more geometric. So it has the advantage of being like quite robust. Well, not very robust, but in the sense that you can extend it to slightly beyond the flat initial data condition. So we can take some boundary functions. So it takes some pi on the defined, which is a function defined on the line x plus y equal to 0. And then you define the passage time to RR with this boundary condition as the maximum over all the starting points plus this boundary condition. And also the same for the passage time to NN, so that you have this maximum passage time with the same boundary conditions. Then for this XR pi and XN pi, we can show that using the same arguments, the covariance of them has the same behavior, and as tau goes to 0 or 1. Well, why is this? Well, the boundary condition pi needs to be subdiffusive, meaning that when your x moves away from the origin, it grows at most x to some polynomial power, and that the power is strictly less than 1/2. Okay, so why is that? Because like as you say, that the thing that prevents us from applying our arguments to general initial data condition is that we use that for the area 2 process, or like the point to line profile, as one moves away from the maximum, it decays square root in the distance. So as long as the boundary condition you add grows slower than that, then that would be overcome by that decay. So the same argument would go through. So this gives you some slightly more general results. Well, whereas like if this boundary condition is not subdiffusive, like for example, if you take S very close to 0, like it becomes diffusive, then one would expect some different behavior would happen, and there might be a phase transition there. Okay, the second comment is about the more technical aspect of the proof. So for the upper bound, we wanted to remove this extra factor of exponential minus log tau times to the 5/6. Well, so basically the thing that we want to bound is the following probability. So it's a probability that the area 2 process, the maximum is within some interval I. So ideally, so as for the Brownian motion, you see that this should be bounded by the constant times the length of this interval. And that's indeed the case for the Brownian motion. But for the area 2 process, we don't know how to do that directly. So we resort to this Brownian comparison and losing the factor of exponential minus log I to the 5/6. But if we can prove this directly, then we can remove this extra factor. So something we attempted is to work with the formulas of the area 2 process, where we find them not very easy to analyze. And in particular, there are some difficulties in dealing with some large deviation scheme, so that when the maximum is very large or small, and I remember in particular when this maximum is very small, so that the point line passage time is very small, then in that case, the profile would look quite different from like a Brownian motion. And then this makes it really hard to analyze and really hard to bound this probability. So so that's something that we don't know how to do. And it would be great if some analysis of the area 2 process directly can give this. Yeah, and I think that's it. Yeah, thank you.
Okay, thank you very much, Lingfu.
Okay.
Let's see if somebody has some questions. So I'm going to start with a question. So in your main theorem with that you presented at the beginning about the rho, so sometimes you stressed about universality when tau.
Oh, you mean this one?
Tau goes to 1 or 0, but so from the argument you presented, I mean, can you expect if this rho is universal itself?
You mean this rho?
Mm-hmm.
So actually, that's not universal. Like, I mean, so this is only for the flat initial data case. It's not for the. That's not for the. Okay, so the existence of this limit is proved by Ferrari and Spohn in that work. So while as like this can depend on the initial data condition. So if you take like yeah, of course, like for the step initial data condition and the flat initial data condition, the tau goes to 0 behavior is different, right? So you can imagine that it's different in general for different initial data conditions. So here, by this I mean, I guess you were mentioning about this, right? So I mean that this is just by in the work of Ferrari and Spohn, they showed that when tau goes to 1, the behavior of this covariance is always like this. So it converges some constant minus an error term in the order of 1 minus tau to 2/3, no matter what the condition is. So it can be flat initial condition or step initial condition or like the random initial condition of the, which is the stationary initial condition. But like, for example, the constant can be different for different cases, but it just is that when tau goes to 1, the behavior is like this. So it just is that the rate of convergence to C is like 1 minus tau to 2/3.
So in this sense, it's universal. Okay.
Yes, that's in this sense. Maybe so I guess universal is not the word that they use in that paper. It's just the word that I use. Maybe it's a bit inaccurate here.
And okay, so just to expand on this question. So for example, if you change at the end you discussed about taking different initial profiles. So in this sense, how is this rho change?
Let me see. I'm not sure. I don't know about that. So while okay, so what we do is that we can have some upper bound. So you see, like we have some upper bound of big C times tau to the 4/3, and lower bounded by some little C times tau to the 4/3. But I don't know about like any more information, any more precise information.
So okay, the upper bound can be done, but maybe there will be some.
Okay. Right. So we just identify that when tau goes to 0, how fast this goes to 0, giving upper and lower bounds which can differ by a constant. And actually, the upper bound will lose a subpolynomial factor. But it's a conjecture by Ferrari and Spohn that it should have this behavior, and they have some non-rigorous like heuristic explanations, which I don't remember exactly what it is, but there was a conjecture there. So
okay, thank you.
So Lingfu, it's very nice work. I really like the results. Can you say more about breaking this subdiffusivity condition on the general initial condition? I mean, if I'm understanding it, I'm kind of imagining something where if you kind of break that, it seems like the question becomes degenerate in some sense, right? Where if you have a certain kind of initial condition that's growing too quickly, then that's just kind of going to govern the whole global structure of things as far as you're concerned. But maybe I'm completely misunderstanding it. So right. What kind of phase transition do you expect?
I would say like when you grow, when you have some deterministic initial conditions and that grows faster than square root, I would expect this power to be smaller than 4/3, because like in the extreme of the step initial data condition, then you have like 2/3, and there should be, but it's unclear for us. Like, okay, that's something that we probably want to do next, about to analyze like what's a phase transition like, but from now on it's not clear. So the reason that that fails is that we here we use that this point line profile decays exponentially. So this is like, okay, you have this point line profile, and then you are some place far from Umax, then you lose a lot in the part of the passage time to NN, and then that can be very hard to be compensated from the passage time to the line x plus y equal to 0. Whereas now you have some initial data conditions, then it's possible that it would be compensated by what's happening here, like because the initial data condition can be large. So
what if your initial data falls really quickly?
Sorry?
What if the initial data falls really quickly? It doesn't grow, but it falls very fast.
Right. So you mean our initial data condition?
Yeah. So actually, I kind of missed what your subdivision is. Your subdivision on both sides or only on the upper bound side?
Yeah, I think it's on both sides. It's on both sides. So we need to use this on both sides. And so our initial data condition is just flat, but we can generalize to like sub diffusive, so it grows slower than square root.
So suppose my initial condition is like minus x cubed, so it's decaying really quickly. Is that covered?
Let me see if it's that's not because we need to analyze, okay, so this Umax is somewhere here, and that compared to so you don't know where that is, so you know what, so that's not covered. Even that is not covered. We cannot do that even with like one side bound. So cause like with some like fast growing or decaying boundary conditions that can make the whole geometry look different, like where this endpoint of this point line geometrics end, that can be like far from being like uniform anymore. So that may also depend on how the boundary condition looks like. So that basically just requires some more geometric analysis, I suppose.
I had another question. Sorry if I interrupted, Eric, if you had something else to ask. Okay. So here you're starting from one line and you're looking at one point to a different point. So that's like one coupling of for line to point things. What if you started, right, you fixed your point and you had different lines?
I would say that would be, that's more like tau to the 2/3, I think.
I see. Yes, it'll be very similar to the point to point case, I see.
Yes, that would be similar to the point to point.
Okay, because it happens in the beginning. I see.
Yes, it happens at the beginning, and then that would definitely overlap with constant probability, and that gives you a factor of R to 2/3.
Okay.
So I guess the main difficulty here, like compared to the point, is that the exponent is larger, so the covariance is much smaller. So using some other approaches, it might be very difficult to like there are some too much error terms and it would be difficult to analyze as small things. So that's why that people first do the point-to-point ones.
So for the Brownian case, there is a like a conjectural like limit for by Ferrari and Spohn, right? Like when the initial data is a Brownian initial data, like a stationary initial data.
Right.
And that is different from like even from the flat. I think that's probably same as the one for Narrowich or step initial data.
Right. That's the same. I think that's already verified in this work, Ferrari and that's already verified. And using their approach, they can have very like precise formulas for like what's the covariance like. It's not just a bound. They can have very precise order of the covariance, I think. But okay, so there is another thing that's interesting is that you see that for the stationary, so you take a Brownian motion or take a random walk there, that grows actually diffusively.
Right.
Right, but that's different from like if you take a deterministic boundary condition. So because there is some randomness that cancels out some covariance. So that's sort of different. And
but then if they like take like sort of a Brownian plus a drift or something, is there like any hope one can do that or?
Yeah, I think for Brownian plus a drift, that's I think that's something. So if your initial data is random, then so when you compute the covariance, that averages out something. So I would expect that one can do that using approaches similar to what they did there.
So I have another question. So usually so you consider the point to line case, and okay, in general this is there is a model that is exactly solvable, but another case that is exactly solvable is the point to half line case. Are you aware of any work in this about time correlations in this case?
I haven't thought about that. So you mean the half line? So it would be like you have the one
only
slope,
on half,
and then you have a flat on the other side.
The line, this flat on the other side.
Yeah. I would say that would be so a similar like geometric analysis would work, and I think that would behave pretty like this point line case is taught to the 4/3. I haven't thought about that before, but let me see. But when analyzing that, like if using our geometric arguments, we actually do not need like exact solvable input for the half line things. It's just like so the exact solvable input that we use are just this. So
yeah, so you just using this these two things and the properties of the area to process.
Yes, and the property of the area to process, right.
So in this sense, maybe this question they ask is covered using by different initial data to set at the end.
Right. But that's not exactly the same, because like in other, so it's like the initial data you have like a flat in one half, and then you have the jump in the other half. but I suppose that some similar geometric arguments would also give you something like that. I may need to think more about that, but I expect that the similar geometric arguments, like maybe some more careful analysis in some, because like you cut something, then you only have last passage restrict to some shapes, but I would imagine that does not change much. I mean, a same spirit thing would work in that case.
I think like in the half space last passage percolation, I'm not sure like if you can use like this Brownian Gibbs property, like because in the half space, if you restrict the parts in the half space, it's, I don't know if someone proved like this.
Oh, I see what you mean. I see what you mean. Right.
Because it always has this constraint on like
right
on the diagonal. So
but I would expect like you only need to use you don't actually use the point line profile for the half line. You just use the point line profile for the whole line. You just don't look at the half. Is that does that make sense?
Yeah, if that is so, then I think one can do that. But like if the whole part would see the constraint on the diagonal, then
oh, I see what you mean.
Model half line initial condition, or like half space only above the diagonal you're allowed to do things?
That's so half space. If it is half space, then I think like it's a problem. But
yeah, for half space, if you just chop the half space rather than just chop half of the initial condition, then that would be different, I guess. Yeah, I agree. That would be completely different.
Of course. So when I say exactly solvable, it's just I mean that for exactly solvable case, maybe you can expect to have a nice formula for rho. That's why I say exactly solvable. Of course, I understand that yeah, these techniques do not require any determinant formula.
Right. But we use estimates. Like, for example, we cannot do the same thing for like first passive percolation or general weights.
Well, okay, let's see. Probably there are no other questions. Okay, so in this case, let's thank Lingfu again. Thank you very much for this.